To calculate Earth's curvature, DeLambert and McCain employed the principle that Earth is approximately spherical, enabling its curvature to be determined using triangulation across extensive distances. When measuring over long spans, the Earth's curvature causes slight deviations in angles between surveyed points compared to what would be expected on a flat surface. Though small, these deviations are measurable over considerable distances, such as the span between Dunkirk and Barcelona. Their approach involved measuring two straight roads with precision instruments, such as metal rods, to establish a baseline for further calculations. The method hinges on spherical trigonometry, a mathematical discipline that accounts for the Earth's curvature when evaluating the angles and distances within triangles on a spherical surface. The curvature affects the sum of the angles in a triangle, which, unlike in planar geometry, exceeds 180 degrees on a sphere. DeLambert and McCain utilized the measured baseline, the two roads, and calculated angles between survey points to model the Earth's curvature. From these measurements, they derived Earth's radius using geometric principles and subsequently calculated its circumference using the formula, c equals 2 pi r. Triangulation, a critical concept in their calculations, requires at least one known baseline, forming one side of a triangle. The process involves connecting this baseline to additional points and measuring the angles to form interconnected triangles. Once the baseline is established, the lengths of other sides can be determined from the measured angles, allowing for the creation of a network of triangles. These interconnected triangles enable the extrapolation of measurements over a larger area. For DeLambert and McCain, the two roads served as the foundation for this network, enabling them to calculate distances and angles across a vast region, ultimately determining the distance from Dunkirk to Barcelona and beyond. This process is analogous to modern techniques like laser scanning, where depth and surface geometry are measured by creating a mesh of triangles. Such methods demonstrate the enduring relevance of triangulation in fields ranging from geodesy to 3D modeling. The concept of a baseline in triangulation extends beyond physical measurements. It serves as a metaphor for broader scientific and philosophical endeavors. Establishing a foundational baseline, be it in measurements or conceptual frameworks, is essential for achieving clarity and making progress. Just as the baseline in a Cartesian coordinate system provides reference points for calculations, foundational principles guide the exploration of complex ideas. Geometry offers profound analogies for human aspiration and progress. Consider a cube, stable and grounded with its equal faces and sharp edges resisting external chaos. The cube, however, metaphorically, yearns to transcend its form, narrowing and rising into a pyramid. This transformation, from a grounded shape to one focused at an apex, symbolizes a movement toward unity and higher purpose. The pyramid's apex concentrates energy and potential, representing the culmination of ambition. Yet this ascent is precarious. Its stability depends on the integrity of its broad base. A single destabilizing force at the foundation can lead to collapse, illustrating the delicate balance required in both structural and metaphorical growth. The reflective properties of structures like pyramids and parabolas offer further insight. The parabola, defined as the set of points equidistant from a focus and directrix, demonstrates how abstract mathematical principles manifest in practical applications. Its reflective properties concentrate electromagnetic waves at a focal point, enabling efficient technologies like satellite dishes. Similarly, the pyramid's apex can be seen as a focal point for energy and potential. This concept has fueled theories about the Great Pyramids of Egypt, speculating that they might have served as hubs for energy generation, though evidence for such claims remains speculative. In both cases, these structures represent the interplay between reflection, focus, and transcendence. A reflective pyramid mirrors its environment, connecting internal essence to external realities, while a transparent pyramid allows light and understanding to penetrate, revealing inner truths. This interplay highlights the dual nature of growth, anchored in stability yet striving for higher aspirations. The exploration of Earth's curvature and the geometric methods involved can also be linked to broader intellectual themes. For example, just as DeLambert and McCain had to accept and work within the framework of Earth's spherical geometry, advancements in mathematics required openness to previously dismissed ideas. Early mathematicians like Jerome Cardano rejected the notion of imaginary numbers as nonsensical, while others, like Raphael Bombelli, embraced their utility, paving the way for advancements in complex mathematics. This openness to challenging established frameworks echoes the spirit of triangulation, using known foundations to explore and map the unknown. From Earth's curvature to mathematical transcendence, the principles underlying these explorations reflect a common theme: the pursuit of understanding through foundational measurements, reflection, and transcendence. Whether through the precise triangulations of D'Alembert and McCain, the reflective geometry of pyramids and parabolas, or the intellectual humility required to embrace new ideas, progress is rooted in a balance between stability and aspiration. These processes reveal the interconnectedness of mathematical, physical, and philosophical domains, illustrating the profound impact of foundational principles on the quest for deeper truths. The concept of unity between horizontal and vertical dimensions demonstrates how disparate elements can merge into a cohesive and functional system. This unity reveals that openness to abstract ideas fosters clarity and innovation. By embracing seemingly unreasonable or abstract principles, we uncover deeper connections between fields of knowledge. Consider the cube as it morphs into a pyramid, a transformation that amplifies certain qualities and focuses energy toward the apex. This apex, much like the focal point of a satellite dish, becomes a singularity where the many converge into one. This shift is not merely a simplification, it is a magnification of form and purpose. The transformation of the cube into a pyramid and then into a cross introduces another dimension entirely, representing both physical and metaphysical elevation. When a base is sacrificed, it gives rise to a new form, a new foundation, birthed from both the ascent and the reflective properties of the cube. The reflective and transparent nature of the cube allows light to bend and refract, creating new structures. Light, at its essence, becomes the source of these formations, symbolizing the birth of new ideas, aspirations, and concepts. In this transformation, we find a parallel with the idea of heaven, an emergent state requiring sacrifice. The cross, as a culmination of this transformation, symbolizes the meeting of dualities, the horizontal plane of earthly existence and the vertical plane of divine aspiration. It is an emblem of sacrifice, representing the deliberate breaking of stability to foster new life. This process of sacrifice is akin to controlled chaos, destructive, yet generative. The cube's opening reveals its orthogonal axes, which form the foundation for new directions. The cross, born from this ambition, acts as both a gateway and a map of transcendence. In the cross, the sacrifice of the base is not a loss but a transformation, where structure becomes spirit, and the static becomes dynamic. The thought process here is recursive. The cube, in its desire to transcend, must break open, revealing both its potential and its fragility. The vertical axis becomes a symbol of ambition and spiritual ascent, requiring both aspiration and destruction. Through the fracture of stability, new possibilities emerge, bridging geometry, philosophy, and the very essence of life. Metacognition plays a pivotal role in this philosophical framework. By examining the object of our perception, we unlock new doors through projections of light. These projections remind us that we, like the cube, are reflective bodies. Every external form we perceive acts as a mirror, reflecting aspects of ourselves. This mirroring process drives us toward the apex of our potential. However, if we fail to engage with these reflections alchemically, transforming and redirecting the light toward higher aspirations, the entire structure falters. The cube, as a metaphor for existence, embodies the interplay of light and dark, reflection and projection. It becomes a receiver, alchemist, and reflector. This interplay reveals portal-like thoughts and doorways to untapped potential. The cube is a three-dimensional structure defined by its XYZ coordinates, representing the relationships and interactions of matter. To become aware of the cube's reflective nature is to become a multidimensional observer. This awareness transcends physical form, inviting philosophical inquiry and spiritual elevation. The journey from the cube to the cross exemplifies a movement from groundedness to transcendence, from structure to sacrifice. Each stage represents a shift in perspective and purpose, urging us to embrace the recursive nature of growth and transformation. Expanding this concept into a broader geometric framework, the study of triangular meshes offers insights into creating interconnected systems. These meshes, formed by edges and vertices, exemplify the idea of building complexity from simplicity. As we delve into spherical geometry and trigonometry, the relationships between angles and distances on curved surfaces provide a deeper understanding of three-dimensional space. Spherical trigonometry, for instance, helps translate angular relationships on a sphere into actionable knowledge in 3D space. This step builds upon basic trigonometry in triangular meshes, pushing the boundaries of what we can conceptualize and calculate. The iterative nature of this process mirrors the philosophical journey, refining methods, equations, and ideas, even as we sacrifice outdated concepts for more advanced understandings. The unity of horizontal and vertical dimensions, embodied in the cube's transformation, represents a profound philosophical and geometric journey. From the reflective properties of the cube to the sacrificial emergence of the cross, this process illustrates the interplay of structure and spirit, destruction and creation. As we project and reflect, we discover not only the light within but also the pathways to transcendence. Whether through geometry, philosophy, or life itself, the pursuit of growth demands both ambition and the willingness to let go. This recursive process invites us to transcend stability and embrace the transformative power of sacrifice. When working with curved objects, such as a spherical body or any rounded shape, spherical trigonometry is invaluable for determining the shortest path between 2 points on the surface. This shortest path is known as a great circle. Great circles are fundamental because they represent the largest possible circle that can be drawn on a sphere, and they provide the basis for understanding spatial relationships and angles on spherical surfaces. The great circle is formed by the intersection of the sphere with a plane that passes through its center. Calculating the shortest path between 2 points on the surface of the sphere inherently involves this concept. The curve of the great circle reflects the natural geometry of the sphere, making it vital for understanding how points, angles, and paths interrelate on a curved surface. To calculate these paths, we need 2 points on the sphere. The relationship is similar to determining the radius of a circle based on the unit circle. When 2 points are connected via the shortest path, the resulting arc lies along the great circle. This arc is a curved segment representing the natural geometry of the sphere's surface. The great circle can be seen as analogous to the equator of a sphere, splitting it into 2 equal hemispheres and representing its maximum circumference. When working with irregularly curved surfaces, such as a human body or an asymmetrical object, the process becomes more complex. For this reason, advanced methods like tracing and scanning technologies are employed. These methods use tools such as lasers and dot matrix grids to map the surface accurately. A body scan, for instance, involves capturing data points across the surface, which can then be used to calculate shortest paths and define endpoints. These endpoints are derived directly from the traced contours of the body. A key computational method used in these cases is Delaunay triangulation. This is a process for dividing a surface, whether flat or curved, into triangles. The principle behind Delaunay triangulation is to ensure that no point lies inside the circumcircle, the circle passing through all 3 vertices of any triangle in the mesh. This creates a network of non-overlapping triangles that can be used to model complex 3D surfaces from a set of 2D data points. The triangulated mesh provides a well-formed structure that is ideal for representing curves or irregular surfaces. To achieve this, 1. Data points, measurements or data points are taken along the surface. 2. Triangulation, these points are connected into triangles using Delaunay's method. 3. Mesh creation, the resulting mesh approximates the curve or surface of the object. On spherical surfaces, the triangles may approximate arcs of great circles, which are essential for accurate modeling. These arcs represent curved paths and are instrumental in understanding the geometry of the surface. For applications like body scanning, these arcs become critical for creating patterns. Body scans highlight specific arcs, which can then be directly mapped to the patterns used for designing garments or other fitted materials. The arcs are analyzed based on angular measurements, considering factors such as the drape and fit of the fabric. By using gradients, a unit of angular measurement, the process becomes more precise and computationally efficient. While traditional trigonometry often relies on radians, gradients offer advantages, particularly in pattern design, because they work with whole numbers instead of fractions. This simplifies calculations and avoids some of the complexity associated with radians and pi. Radians divide a full circle into 2 pi units, while gradients divide it into 400 units, providing a decimal-friendly system. This contrasts with the more traditional 360-degree system, which has its roots in ancient Babylonian mathematics. The Babylonians based their system on the number 60, leading to the division of a circle into 360 degrees, 60 by 6. This historical context demonstrates how mathematical conventions often arise from tradition rather than efficiency. Using gradients aligns better with modern computational needs, particularly when translating bodily curvatures into patterns. This system allows for easier coding, better precision, and more streamlined workflows. Additionally, it avoids unnecessary complexity and redundancy, making it ideal for designing precise fits for irregular shapes like human bodies. The historical roots of our mathematical systems influence many modern practices, even when alternatives might be more efficient. For example, the 360-degree system remains dominant because of its historical legacy, despite the existence of more practical systems like gradients. Mathematics, much like language or religion, evolves with culture and human nature, resulting in disagreements about which approaches or equations are best suited for specific tasks. The adoption of new systems, like gradients over radians, reflects a willingness to break from tradition and prioritize utility and efficiency. This evolution is a reminder that even the most fundamental aspects of math and science are shaped by the choices of earlier civilizations. To fully understand the concepts in this transcript, it's important to look at a few key ideas and their interconnections. Modern society, particularly in the United States, stands out for its innovation and progressive embrace of change. One aspect of this is its acceptance of immigration, which brings in new ideas and fosters cultural diversity. However, there is a concern that homogenization, or the loss of diversity in a society, can lead to stagnation. When a culture becomes too comfortable with its existing traditions, it can stifle innovation, leading to a metaphorical swamp where nothing changes. This stagnation is often referred to as the need to drain the swamp, a concept famously echoed by Donald Trump during his campaign. The idea is that without continual innovation and adaptation, society becomes too comfortable and loses its momentum. A key tool to explore innovation and understand how things evolve is geometry, particularly in how we model and understand space. For example, when studying curved surfaces, such as spheres or other non-flat shapes, we often use circles as a more accurate way to model these surfaces instead of relying on triangles. While triangles serve as a good starting point for conceptual models, they can't fully capture the complexity of curved regions. This is where spherical trigonometry, which uses the properties of circles, becomes essential for accurately describing the relationships on curved surfaces. The conversation then shifts to the role of trigonometric functions, particularly sine and cosine, in modeling these curved regions. These functions are fundamental for understanding how points move along circles and spheres. In the context of my own content, whether in discussions about cars or tech farming, these functions are crucial for understanding things like voltages and electrical signals. The sine and cosine functions describe periodic, wave-like behavior, representing the oscillations of points along a circle or sphere. These oscillations are crucial for calculating positions in space, as they help determine the x, y, and z coordinates of points in various systems. It's important to note that sine and cosine functions are not just abstract mathematical concepts, they reflect the fundamental nature of reality. Everything in the universe, from light waves to electrical signals, can be described by waves and particles. Sine and cosine functions help model these waves' behavior, showing how they oscillate up and down, or side to side. This mirrors the behavior of electric voltages, sound waves, and even light waves. The periodic oscillations modeled by these functions reveal underlying properties of the universe, where everything can be understood as either a wave or a particle. These oscillations are driven by angular motion, which ties back to the circular nature of the unit circle. The unit circle is a fundamental tool in trigonometry, used to represent the relationships between angles and the sine and cosine functions. By mapping these oscillations in terms of both time and space, we can create a coordinate graph with the x-axis representing time and the y-axis representing amplitude or space. In the context of waves, amplitude refers to the strength of the oscillation, or the magnitude of the wave's effect. The x-axis represents time, and the y-axis represents space, or amplitude, but when combined, they reflect both time and space as a single system. This relationship connects directly to general relativity, where time and space are intrinsically linked. The sine function corresponds to the vertical oscillation, the y-coordinate, and cosine corresponds to the horizontal oscillation, the x-coordinate. Together, these two functions provide a complete picture of how waves behave over time and space. At a more practical level, understanding these concepts allows us to visualize how systems work in both mathematical and physical contexts. When we place a point on a graph, the sine function dictates the vertical motion, up and down, while the cosine function governs the horizontal motion, side to side. The angle theta is measured from the positive x-axis, and this angular measurement is fundamental in understanding the relationship between the sine and cosine functions. This framework allows us to understand the dynamics of waves, oscillations, and the physical world in a unified manner. In sum, by combining our understanding of geometry, trigonometry, and wave behavior, we can begin to see the connections between the abstract mathematical world and the physical universe. These concepts are not isolated but instead reflect the underlying structures that govern both our physical reality and our intellectual pursuits, such as the work of polymaths like Leonardo da Vinci. The ability to draw connections between disciplines is central to innovation, and it's this interdisciplinary approach that powers forward the advances we see in modern society. The spirit of polymathy, as embraced by Gen Z and others, drives innovation by drawing on a wide range of knowledge and recognizing the interconnections between seemingly disparate fields. This way of thinking, embracing both the complexity of traditional disciplines and the dynamism of new, interdisciplinary methods, mirrors the way we approach scientific and technological advancements today. Whether we're modeling the universe using trigonometric functions or exploring the deeper patterns in nature, the goal is to find the underlying unity that connects everything. Just as sine and cosine functions provide a mathematical representation of wave behavior, understanding these interconnected concepts gives us a richer, more cohesive view of the world around us. When plotting sine theta, or cosine theta, imagine how these functions behave as the angle increases. If you think of this graph in terms of circular motion, where the angle represents the position on a circle, the sine and cosine functions describe how that circular motion projects onto a straight line. These oscillations, which alternate between +1 and -1, represent the vertical, sine, and horizontal, cosine, components of the circular motion. If you think of this in terms of the unit circle, a circle with a radius of 1, the sine and cosine functions capture the oscillations along two perpendicular directions, one vertically, sine, and the other horizontally, cosine. These oscillations mirror how Cartesian coordinates break motion into perpendicular components, representing every possible direction of oscillation in 2D space. Together, sine and cosine provide a way to tie circular motion to linear waves. To understand this better, let's consider how sine and cosine help calculate the coordinates of points on a circle or a sphere. These functions are useful when working with curves, allowing us to easily translate circular motion into a 3D model. By applying a scale factor, we can move from this 2D representation to a more accurate 3D model. For example, if we imagine a person standing beside a measuring tape on a flat wall, we can use that as our baseline. The scale factor, much like how it's used in CAD design, is essential for translating real-world measurements into 3D space. Without this factor, we lack a reference to scale the other elements of the model, which would make the measurements meaningless. In CAD design, scale factors are crucial when converting 2D data, like photographs, into 3D depth information. This process gives us a true sense of the proportions and depth of the objects we're modeling. For instance, if we know the height of a person standing by a measurement line, we can extrapolate the size of other points in the image by using this known reference. Extrapolation in this context means extending our existing measurements or trends to predict unknown values, assuming the relationship between known and unknown variables will remain consistent. By using this scale factor, we apply a known measurement, such as the height of the person or the distance between 2 points, to map out the dimensions of the object being modeled. It's like tracing the body or an object using a parametric model. This brings us to the concept of parametric modeling, which we previously discussed in part 1 of our algorithm video series. Parametric modeling allows us to describe irregular shapes and complex curves by starting with simpler, well-understood geometries such as rectangles, cylinders, or spheres. Using these basic shapes, we can create more complex models. For example, artists or designers often begin with a basic shape, like a circle or rectangle, and then refine it by adding curves and adjusting for irregularities. This process allows them to maintain precision while gradually increasing the complexity of the model. In computational modeling, this idea translates into using coordinate systems like cylindrical, spherical, or rectangular to describe complex shapes. By leveraging the simplicity of basic geometric primitives, parametric equations enable us to break down complicated shapes into manageable parts. This method of starting with simple shapes is similar to how artists build up their work, starting with basic proportions and blocking out the general shape before refining details. In CAD drafting, this approach is similar to how we create 3D models from 2D drawings. The software typically automates this conversion, but if you were doing it manually, the process would involve using these fundamental principles of scale and parametric modeling. For instance, in AutoCAD, you begin with basic shapes, lines, circles, ellipses, or rectangles, and build from there. These shapes act as a foundation, and once the base structure is established, you can then refine it with curves and other details to represent the final form more accurately. This method of working from a base shape is essential in CAD design, as it ensures that the final 3D model is both accurate and precise. In the same way that artists work within known proportions and measurements, CAD designers must follow precise guidelines, taking into account the scale factor, the starting point, and the relationships between elements. Whether in architecture, engineering, or product design, using simple geometric shapes as a foundation ensures the accuracy and integrity of the final model. This is why precision and a solid understanding of scale are fundamental in any modeling or drafting process, allowing us to represent real-world objects accurately in a digital space. 1. The explanation of extrapolate could be clearer by defining it more explicitly early on before using the term in a practical example. The original text uses extrapolate without a definition, which may confuse some readers unfamiliar with the term. 2. The transition from unit circle to parametric modeling could be smoother, linking the idea of circular motion to real-world applications more clearly. While the idea of using scale factors and parametric modeling is good, a more direct connection between these concepts might help readers see the overall framework more easily. 3. The mention of Fir'mv Morse algorithm seems out of place without explanation. A brief reference to what this is or how it fits into the larger discussion of parametric modeling would provide better clarity. The foundation of our understanding of complex systems often lies in their roots, much like how human evolution traces back to early life forms, such as fish. This analogy reflects how we build upon simpler ideas, often without fully grasping their origins. Similarly, our cognitive processes and most precise logical applications can be traced back to the way we form and use language. The words we choose, their meanings, and their structure provide a window into the underlying logic of our thinking. For example, homophones and homographs, words that sound the same or are spelled the same but have different meanings, are common in the English language. While the history of the English language is vast and complex, its ties to ancient languages like Latin and Greek, and even more recent cultural shifts, shape how we understand and communicate ideas. English, in particular, is deeply influenced by religious and philosophical frameworks, especially Christianity, and these influences are ingrained in the language itself. Additionally, the evolution of the language and its usage can also be tied to more modern scientific ideas, such as Darwinian principles, which reflect our changing beliefs about the world. These dynamics in language provide insight into the beliefs of individuals and cultures, shaping the way we see and interpret the world around us. This interplay between language and belief makes it crucial for individuals, especially those engaged in creative or intellectual work, to be interdisciplinary in their thinking, incorporating diverse perspectives. The words we use and the beliefs they carry are essential to understanding who we are and how we view the world.